Hello, I am Ali Muhammad Zubair. I am a graduate student at South Dakota School of Mines and Technology. Currently, I am working in the switching power conversion lab under the supervision of Dr. Malik Ramajani. Today, I am going to talk about my research on phase lock lobe based synchronization for single phase and three phase DC to AC power converter application. The main goal of our research is to design synchronous reference frame PLL that is capable of tracking system frequency even under high frequency variation. This project is funded by Phase Technology LLC, which is a power electronics manufacturer located in Rapid City, South Dakota. Now I am going to show you the whole experimental setup. This is single phase to three phase converter which takes single phase supply from the grid and generates three phase square wave output voltage. This is LC filter which actually filter out the high frequency component from the square wave and generates sinusoidal voltage. These are the output of the LC filter which is connected to the input of the control card. This control card has developed by Phase Technology. It is similar to the control card used for the phase converter. This is the microcontroller of the phase control card. It is Texas Instrument C2000 series microcontroller. The communication between control card and computer has done by XDS 200 emulator to load program to the microcontroller. This is the auxiliary power supply to power up the control card. This step-up transformer is used to supply 240 volt to the auxiliary power supply. Here we measure our input voltage using differential probe which is connected to the channel 1 of the oscilloscope. Channel 2 is connected to the output of the PLL. The whole code is written on Code Composer Studio. This time I am going to demonstrate the difference between the experimental result of zero crossing PLL and our proposed SRF PLL. First I will show you the zero crossing PLL. Here zero crossing PLL is running. Let's see what happened at 60 Hz. At 60 Hz, if you look at the oscilloscope display, you can see this PLL is able to lock at 60 Hz. Here UL1 is the channel 1. It is displaying input line to line voltage, and blue one is the channel 2. It is displaying output of the PLL that generate a pulse when input voltage crosses from negative half cycle to positive half cycle. Now we will see the response of the PLL for higher range of frequency variation. If I increase the frequency, for example, 67 Hz, if you look at the oscilloscope display, this PLL cannot track the high frequency variation, therefore it cannot detect the zero crossing. Let's see if we decrease the frequency. If we decrease the frequency, for example 53 Hz, similar thing happen. This PLL cannot track the frequency variation, therefore it cannot detect the zero crossing. This time I am going to demonstrate the experimental result of our proposed SRF PLL. Here SRF PLL is running. Let's see what happened at 60 Hz. At 60 Hz, if you look at the oscilloscope display, you can see this PLL is also locked at 60 Hz. Now we will see the response of our PLL for more than 10 Hz frequency variation. Now, if I increase the frequency, for example 73 Hz, you can see this PLL can detect the high frequency variation, therefore zero crossing is detected correctly. Let's see if we decrease the frequency, for example 47 Hz, you can see similar things happen. And this PLL is also detect the high frequency variation, therefore it can detect the zero crossing correctly. So we can conclude that our proposed SRF PLL can provide perfect frequency track under high frequency variation. Thanks for watching.